The topic for discussion is states of process and process state diagram. So, what is a process in an operating system? In an operating system, a process is a program or set of instructions that are currently being executed. It is a fundamental concept of modern operating system and it is managed by the operating system's kernel. Each process has its own memory space, which includes instructions, data, and stack. It also has its own set of system resources such as CPU time, IO devices, and files. So let's distinguish between a program and a process. A program is a set of instructions that has been designed to complete a certain task, whereas a process is an instance of program that is being currently executed. A program is a passive entity, whereas a process is an active entity. A program is considered as a static entity, whereas a process is a dynamic entity. A program does not require a control block, whereas a process has its own control block, which is called as process control block. A program requires memory space to store instructions, whereas a process requires CPU resources, IO devices during its execution. Let's talk about some operations on process in an operating system. The first operation is creation. Once the process is created, it will be ready and come into the ready queue and will be ready for the execution. The next operation is scheduling. Out of the many processes present in the ready queue, the operating system chooses one process and start executing it. Selecting the process which is to be executed next is known as scheduling. The third operation is execution. Once the process is scheduled for the execution, the processor starts executing it. Process may come to the blocked or wait state during the execution, then in that case, the processor starts executing the other processes. So let's talk about states of process in OS. The first state is new state. A program which is going to be picked up by the OS into the main memory is called new state. Here the process is still in secondary memory and not in random access memory. Degree of multiprogramming is being controlled here by the long-term scheduler. The next state is ready state. Whenever a process is created, it directly enters in the ready state in which it waits for the CPU to be assigned. The OS picks the new process from the secondary memory and put all of them in the main memory. The next state is running state. One of the processes from the ready state will be chosen by the OS depending upon the scheduling algorithm. Hence, if we have only one CPU in our system, the number of running processes for a particular time will always be 1. If we have n processors in the system, then we have n processes running parallelly in the OS. The next state is block or wait state. From the running state, a process can make the transition to the block or wait state depending upon the scheduling algorithm or the intrinsic behavior of the process. The next state is completion state or termination state. When a process finishes its execution, it comes in the termination state. All the context of the process which is stored in the PCB or process control block will also be deleted. The next state is suspend ready. A process in the ready state which is moved to the secondary memory from the main memory due to the lack of resources, mainly primary memory or RAM, is called in the suspend ready state. If the main memory is full and a higher priority process comes for the execution, then the OS have to make the room for process in the main memory by throwing the lower priority process out in the secondary memory. This process is called as swapping of the process. The suspend ready processes remain in the secondary memory until the main memory gets available. The last and the final state is suspend wait. Instead of removing the process from the ready queue, it's better to remove the block process which is waiting for some resources in the main memory. Since it is already waiting for some resource to get available, hence it is better if it waits in the secondary memory and make room for higher priority process. These processes complete their execution once the main memory gets available and their wait is finished. So let's discuss PSD, which is process state diagram. The first state is the new state where a process is just created and not placed in RAM. It is still in ROM and then moves into the ready state. So the number of processes in the ready state is known as the degree of multiprogramming, which is controlled by the long-term scheduler. The next state is the run state. In this state, the CPU is allocated to the processes by the operating system. And the final state is termination state. Here, the short-term scheduler is required to dispatch the processes from the run state to the termination state. From run state, if the process requires some IO device, then it's moved to wait block state. In this state, the process completes the IO request and then waits in the suspend wait state. The main reason behind this transportation of state is the lack of RAM or main memory. That's why we have to move some of the processes from wait block state to suspend wait state. Now, from suspend wait state, we move the process to the suspend ready state. Why? Because if we place in the process again into the wait block state, then it may lead to starvation. From the suspend ready state, then we move the process to the ready state, and then the process follows the normal discourse of run and termination states. So what is a PSD? A PSD is a graphical representation of the different states of a process in an operating system. It is represented as a state transition diagram. It shows the transitions between different states of a process. The diagram consists of circles that represent different states and arrows that represent transitions between them. The different states of the process are depicted in the circles, and the arrows represent the transitions between the states. The transitions are triggered by certain events such as process being created, a process being blocked, or a process completing its execution. In PSD, the transitions are labeled with the events that cause them. For example, a transition from the ready state to the running state may be labeled with CPU allocation, indicating that the transition is triggered by the CPU allocating time to the process. The PSD is a useful tool for us in order to understand the behavior of the processes in an operating system. It helps in visualization of the sequence of events that occur during the execution of a process and understanding the different states that a process can be in at different points in time.